Let us start our second talk. The next speaker is Xiaomeng Xu from Peking University.
Okay, of course, yeah. Thanks for the introduction. It's my great pleasure to come here again. And this is the second workshop on this area and involvability. The first time was last year, about the same time. It was a meeting between PKU and the BINS. And I'm very glad to come back. Could continue our collaboration. And thanks to our collaborations, I had opportunity to visit Schutzenberger in November, and then Moscow in December, and I really enjoyed the visit. And I hope we can continue our collaborations. Okay, so today I'm going to talk about how to construct or how to understand some representation theoretical subjects from the basic theory of differential equation. So roughly speaking, my statement is as follows. So the so-called GON crystals, or the crystal basis of quantum groups, and many combinatorics, many operations on Young tableaux can be naturally obtained from by studying singular perturbation theory of linear ODEs at a singularity. So here, by singular perturbation theory of linear ODE, I mean, so in my talk, I will consider the following in a system of ODEs for n-bound matrix of valued function, where A and B are constant matrix, and epsilon is a small parameter. So this is a typical linear ODE with a second order pole at the origin when z equal to 0. And by singular perturbation, I mean, I would like to understand the behavior of the solutions as epsilon equal to 0. It's a typical perturbation problem. So I hope to show you, to explain you how the combinatorics information arise from epsilon equal to 0 behavior of this ODE. Okay, so this is my main statement, and then in the next 15 minutes, let me explain you all these terms. So first, what's linear ODE about? Because this is the integrability workshop, so I may talk about some analysis. So for linear ODE, I mean scalar for complex valued function fz, where z is the complex variable, and all the coefficients I assume is a meromorphic function on P1. And the typical examples are as follows. For example, f prime equal to a over z times f. A is a constant. Then we know that a solution is given by z power of a, which is a multi-valued meromorphic function that may have a branch at z equal to 0. And another example is given by the Gauss equation or the hypergeometric equation, where A, B, C are again constants. And one typical solution is given by the hypergeometric function that may have singularities at z equal to 1 here. So this is a very typical phenomenon. So actually, a basic fact says that any solution of a linear ODE is a multi-valued meromorphic function on complex plane, and it can only have singularities when the coefficients have 1. So this is the basic fact about the linear system. For the nonlinear system, the solution can have more of singularities than so on. But for linear ones, their singularities are fixed. Therefore, a very basic question you can ask is, what's the asymptotics of a solution as z approach to a singularity? And another initial question you can, but this is a very hard question. Actually, let's consider another example, the so-called Kummer equation, or the confluent hypergeometric differential equation, where A and B are constant, and its solution is given by a formal Paul series form. So here this 1f1 is the so-called Kummer function, and it's given by this Paul series form, where an is the product of a plus 1, and so on. And from this expression, we see that this function is an entire function, except z equal to 0, being its essential singularity. And if we let z go to 0, and to study its asymptotic, find out as z go to 0 from left, then the function behaves like its exponential growth. Well, if you let z go to 0 from the right half plane, then it has polynomial growth. Yeah. So it reflects the so-called Stokes phenomenon that says a function can have different asymptotics as a parameter z go to the singularity, go to a singular point from different regions. Yeah. So this example somehow says that the asymptotics is very hard. It has complicated behavior. And another question you can ask is, so if we multiply a small number in the front of the highest derivative, then what's the behavior of the solution as the equation go to 0? So this is a singular perturbation problem. It's also a hard question because when equation go to 0, the equation, the nth order equation becomes n-1th order. So the equation changes dramatically. So one can imagine its solution will have very complicated behavior. And so these two questions are very natural and appear in many objects, but somehow it's very hard to understand. And today I would like to solve these questions to some extent from a model, from a geometric viewpoint, or actually from combinatorics, tools. So as a baby example, I will first consider second order Poe case, and I will tell you a dictionary between the representation theory of quantum groups or some combinatorics on Young tableau and the theory of ODs at the second order Poe. So in particular, I will tell you how to get the crystal structures out of the singular perturbation. Okay, so this is the first part. First, now let's focus on the simple case. So let's consider following n by n linear system of ODEs for function. Sorry, here this is for invertible matrix valued function. The fz should be valued in capital G O n, not. And U is that U and A are constant. Here I assume U is semi-simple regular. That is, U is a diagonal matrix with distinct eigenvalues, and A is an arbitrary n by matrix. So this is a second order linear ODE. We know that in my previous slides, I consider scalar values nth order ODE, but we know that we can easily transform nth order scalar ODE to a linear system, first order linear system. Therefore, I put in this form, a system form. And so a typical phenomenon for this system is as follows. So we can take any of its fundamental solution Fz. So we take any smooth point, and we fix the initial data at the smooth point. We have a solution. We have a fundamental solution. Then we can let Z go to 0 from different regions. Like in my, in my graph, we let Z go to 0 from left or from right region. Then we will find out their asymptotics are prescript, are characterized by different, invertible n by matrix, what I call T plus and T minus. And in general, it's T plus, just like the Kummer, Kummer function case, is T plus, T minus are in general different matrix. We can take their ratios. We can take the ratios to measure this jump phenomenon of the asymptotics of the solution. Yeah. So this is the so-called Stokes matrices. Again, a linear system with a second order pole has the following typical phenomenon. That is, we take any of its solution and then study its asymptotics around the singularity. Then we will find out the asymptotics the function will have different asymptotics in different surrounding regions. And this different asymptotics can be measured by the so-called Stokes matrices, which are a pair of n by n invertible matrices, S plus, S minus. One can also think of S plus, S minus as scattering matrix from integral system viewpoint. All the internal monodromy data from the meromorphic connection viewpoint. But in any case, we have a transcendental way to assign a pair of invertible matrices to a linear system. And in general, S plus, S minus are highly transcendental functions. It's very hard to understand. Okay, and so now let's first produce you a quantum group from this data. For that, I need to replace this residue matrix A by its non-commutative analog. Recall that here A is an n-by-n matrix with complex entries. Okay. And I will replace this complex entries by the non-commutative analog. So for that, I take the universal looping algebra UGON with n-square generators with commutative relations. Then I take an n-by-n matrix T with entries valued in UGON. So this T is an n-by-n matrix. This T is a collection of generators of UGON. Its ij entry is just the EIJ. And the T, you may recognize T was very often used in the study of quantum integrable system. Or you can say T is a Kading form. And then I can, given a regular semi-simple U or diagonal matrix U, and this T, I can consider the following linear ODE. Now the linear ODE is for matrix valued function, but with entries in UGON. And here I take this H bar as a formal parameters. Therefore, when I take this dot, so to explain why this is how this dot means. So this dot is on the one hand given by the matrix multiplication, and on the other hand given by the product in the universal union. So it explains all the coefficients acting on the solution. And this is I call it a quantum hypergeometric equation, but it's also an example of KZ equation with irregular singularity from different viewpoints. And now we can take, so this equation has the same form as the previous one. Therefore, we can take this so-called Stokes or the quantum Stokes matrices, now n-by-n matrices, but with value in UG. Yeah. So this is a this is a so-called quantum Stokes matrices. So this is a universal setting, but we can also work with a finite dimensional setting. That is, we can take a finite dimensional UG module V, and then we can ask the solutions of this equation, but for function fz valued inside matrix n tensor endomorphism V. To work with a finite dimensional setting. So we can replace this UG by endomorphism V. And then the Stokes matrices are n-by-n matrices, but with entrance valued in endomorphism V. Finite dimensional setting. But in any case, there is a classical theory of ODEs makes you to take Stokes matrices out of this equation. And my first theorem says that this Stokes matrices define your can realize quantum groups. So that is for any fixed regular semi-simple U, the following map is isomorphism between Greenfield-Jimbo quantum group and the undeformed UGON. So recall that the quantum group. Yeah. So here I will not define quantum group very precise form, but it indeed appears in my second part talk. But this quantum group, for those you never seen quantum group, they are just a surjective algebra generated by certain generators, EI, FI, the Chevalier generators. And this theorem says that the map associating the subdiagonal entries of quantum Stokes matrices to the Chevalier generators is isomorphism.
Isomorphism of what structures?
Of associative algebra.
We need to define UGLN over CH.
Yeah. Yeah, this is H bar. Yeah. It's a formal setting is isomorphism. if you specify H bar, to use a pyramidal Q, it's a homomorphism, almost homomorphism. But then, yeah. And in a finite dimensional setting, if I take a finite dimensional UG module, then the following map, defines a representation of quantum group on V. So here, maybe I should recall the Stokes matrix have entrance in UGN, right? Or have entrance in endomorphism V. Here, this map takes the subdiagonal entrance of the Stokes matrix. So in other words, we use the Stokes phenomenon. We use a jump of the symptotics of a linear OD at the central pole to realize a quantum group structure. And this is a starting point. This is a starting point of our study because we know the so given this theorem, you can ask so how to translate the representation theory of quantum groups into Stokes, into the study of linear ODs. Okay, there is some other explanations like from Yang-Baxter equation or complex transaction theory, but let's just skip this. All right, okay. And now let's talk about the crystal structures or the combinatorics on Yang tableau. It's closely related to the first talk. Actually, I do use Gerfeld setting or standard Yang tableau to solve the Riemann-Hilbert problem in the OD setting. And if you remember from the last talk, we have some phases, right? Some inequalities should become equalities from bottom to top, and this both appears in the study of WKB. Yeah. But anyway, so recall that in the theory of quantum group, there is a so-called canonical basis or crystal basis theory. So roughly speaking, if we let the parameter H bar go to infinity, the algebra structure of quantum group will become some combinatorics data of the representations. Or one can say the action of the quantum group on a module V in the limit H bar go to infinity will induce a basis, a certain canonical basis in the module V. And this basis is just a finite set, what I call BV, equipped with 2n-2 operators, the so-called Kashiwara operators, acting on this finite set. And this finite set model on weight basis of V. And on the other hand, in our previous theorem, we realized a quantum group or quantum group actions using this ODE. And so if we look at this linear system, we see that before we have H bar on the right, but we divide H bar, then we get 1 H bar on the left. Then when H bar go to infinity, 1 H bar will go to 0, right? So this is a standard singular perturbation or the so-called WKB approximation for linear system. Therefore, Lustig and Kashiwara's work indicate that the WKB approximation of this linear ODE will produce the crystal structure. So this is an indication. Right? And the WKB methods first appeared in the study of Schrödinger equation in 1926, I guess. Okay, so this is the idea. So why the WKB, why the singular perturbation should be related to crystal basis theory. Okay, let's make it more precise. Yeah, so this is the indication. So our next goal is to realize these crystal structures by studying the H bar go to infinity behavior of the quantum Stokes matrix. Okay, so maybe here let me recall a bit the crystal structure. So as I said, given a finite dimensional representation V, the crystal is just, you can think of crystal is a basis of B with some nice properties. And to be more precise, if we take any semi-simple algebra, but of course in my talk, G is just GUN. But you can, if you take any semi-simple algebra with weight lattice and so on, then a G crystal is a finite set along with the following maps. The first map is so-called weight map. So in the first talk, we have seen this weight map, right? It's a map from the Gerfan setting patterns to the to the sum of the rays, which is exactly the weight map for type A case. And the EI tutor FI tutor, the so-called crystal operators are operators on the finite set. And we have some other maps, epsilon I and phi I from the finite set B to the set of integers with the following relations. Yeah. And this definition, again, this definition is simply by this definition, the definition of crystals is given by studying the H1 or H bar go to 0 limit of the quantum group. So in this limit, the quantum group becomes this combinatorics data. Okay, and now, so this is the crystal side. So what about the WKB side? So what's to be more precise, what's the WKB approximation? So to explain this, let's first when H bar go to 0, sorry, when 1 over H bar go to 0, we are left with this Higgs field, right? So before we have a differential equation, but if this vanishes, we only have an endomorphism. And the spectral data of this endomorphism is the so-called eigenbasis of the shift of argument subalgebra, or the so-called quantized simple fundamental group system. And all one can say, there exists a sort of canonical basis, what I call VI, labeled by index set capital I, of a irreducible representation L lambda. And this basis are parametrized by the semi-standard Young tableau, or parametrized by Gerfan tightening patterns. And this basis are simply the spectral data of this coefficient. So that from the equation, from the analysis, one can say when 1 over H go to 0, the leading asymptotics of this function f will be characterized in some way by the spectral data of this matrix. And the spectral data in our case, that's this eigenbasis. And then let's see how the action, how does the quantum Stokes matrices act on this basis. And then the action of the off-diagonal entries. So recall that in our first theorem, we identify the off-diagonal entries of Stokes matrix with the Chevalier generators of the quantum group. And in the end, we know that the crystal operators are the crystal limit of the Chevalier generators. Therefore, we should study the 1 over H bar go to 0 the limit of this off-diagonal. So how to characterize this behavior? So the action of this off-diagonal entries acting on the set of bases and it takes this form. So each of these sub-diagonal entries is an action on the endomorphism L lambda, on the endomorphism L lambda. And the VI, recall that the VI is a basis. Therefore, this action acting on this basis given by a linear combination of basis vectors. And when H goes to infinity, well, this action will have this WKB or exponential type behavior, where phi ij and gij are certain real valued function. And this H times phi is a real part, while this square root -1, and g is the imaginary part of the growth. So this is a typical behavior. And then, since we are studying the leading asymptotics, right? Therefore, which one are the leading? Which one, among all these coefficients, which one has the biggest leading? Which one is dominant? So we should take the index j such that phi j since phi j is a real number, so we need to take I such that phi j is the biggest one among all the possible j's. Yeah. Therefore, the WKB approximation can be characterized by the following operator ek tilde. So we can define ek tilde in the bottom line. We can define ek tilde acting on vi is given by vj. So here this j is such that the index of phi j is the biggest one. So basically, this operator ek tilde takes the leading, the leading term in the 1OH bar limit. So again, this is a WKB data. So again, we would like to study the 1OH bar go to 0 behavior of this equation. So first, when 1OH bar go to 0, so we are left with the spectral data of this coefficient, which is the eigenbasis of your representation space. And then the subdiagonal entries of Stokes matrix acting on this basis have the following, form. And the leading term is given by the biggest index j. And to encode this j, we define this operator ek tilde. So in the end, by studying this WKB, we get first a basis of your representation space, and then operators acting on this set of bases. So these are purely analysis. Okay, then our second theorem says that this is actually a crystal. This gives you the crystal structure. And this, I cannot fully prove it. I can prove this conjecture under the WKB assumption. That is, so here I cheat a little bit because this behavior is not, we cannot take it for granted. If I assume this behavior, I can prove the following theorem. And this behavior is widely believed. And if I don't assume this behavior, I can only prove this conjecture in a limit case, in the so-called caterpillar limit. Okay. Now let's explain this conjecture and postulate theory. So for any fixed semi-simple regular U, the operators, recall that these operators encode the WKB approximation. These operators acting on the set of eigenbases is indeed a GON crystal. So this is a statement. And here, this limit, recall that this limit I already explained, right? This identities, these limits are explained in the previous slide. And this conjecture is true as UN in the following asymptotic zone. That is, when UN is much bigger than UN minus 1.
This on the norms or the real parts, or UN are complex numbers?
Yeah, here, right, as you asked. So here I should let UN to be purely imaginary.
Okay.
Yeah, or to be real, yeah. There are some analysis issues. Right. And to coincide with known GON crystal structures computed on the semi-standard tableau. Right. Yeah. So here I should comment to prove this theorem. I should solve some Riemann-Hilbert problem or the long-time asymptotics of isomonodromy of certain nonlinear PDEs, and using the Gelfand-Zeitling theory. It really relies on Gelfand-Zeitling theory. So for those who know the shift of argument algebras, like Professor Sharajin is an expert, but he cannot join us today. Yeah. We know that this is shift of argument algebra is a family of maximal commutative subalgebras of UG, parameterized by U. When you go to this limit, this maximal subalgebra becomes a Grothendieck subalgebra. And then the set of eigenbases becomes a Grothendieck basis. Okay. So how much time?
Yeah, right.
20. Okay, great. And one can also realize the tensor product on the crystals, and as well as many, operators, many combinatorial operators on Young tableaux from also Littlewood, Richardson rule. All these combinatorics of Young tableaux can be understood in a purely analysis way. Yeah. But let's skip this. So let's go to the second part, geometry. So put my study in a bigger framework. So what I'm really studying. So, yeah. Before that, any question on part one? So in part one, I show you an example of WKB. How the relation between representation theory and the WKB of linear ODE. Okay. And now let's go to a slightly bigger, a picture. So what I taught is actually a quantification of Riemann-Hilbert map in a differential geometric setting. So now let's solve the linear ODE in a geometric way. The Riemann-Hilbert map, roughly speaking, is a geometric formulation of solving linear ODE. So for example, we can take a linear ODE, n by n system of linear ODEs with n fixed simple poles. And on P1 it takes this form, the meromorphic connection on P1, where A1 to AD are constant matrices. So if we fix the number of poles and the positions of poles, the configuration space of these linear ODEs are just the product of n by n matrices. And this is so-called drum space in differential geometry. And as we have explained, so any solution will be multi-valued holomorphic functions on C1 removing the poles. Therefore, the only interesting transcendental data are the multi-valuedness or the so-called monodromy of the solution. So from the equation side, only the monodromy data are interesting. And these are given by the analytical continuation of any fundamental solution around the simple loops surrounding the poles. And then this analytical continuation produces you the monodromy data. So this is the so-called Riemann-Hilbert map. Basically, this Riemann-Hilbert map takes the transcendental data of your linear ODE, which is a map from the drum space to the space of monodromy data. Here, pi1 is the fundamental group of C removing the poles. And each M1, MD are mono. So we take any smooth point and fix a fundamental solution. Then along a loop surrounding Z1, analytical continuation of any loop surrounding A1 will produce you another solutions at the same smooth point. And the ratio of this solution after analytical continuation and the original one is given by M1 and so on. So this map is the locally analytic isomorphism. It's highly transcendental map between these two affine varieties. But somehow Hitchen in 80s proved that this Riemann-Hilbert map is not just a map, but also a Poisson map or synthetic map. Actually, on the drum space, the drum space is equipped with the famous KKS code structure, while the space of monodromy is equipped with the mechanical symplectic or Poisson structure from the Artia-Bott construction. And Hitchen proved that this is a Poisson or synthetic map. Well, we can also consider general setting, that is ODEs with higher poles. So say D poles, but each pole have degree pi bigger than 1. And then we know that the monodromy data, the topological monodromy data cannot characterize your ODE anymore because at each higher order pole, the symptotics of solutions will jump. You should really take care of this the jump matrix, the Stokes matrix, or the so-called internal monodromy data to characterize your linear system. That is, as I said, the monodromy. The monodromy is sort of topological thing. They are not enough. We really need some complex analysis data. So recall that in the Kummer equation case, we have seen this jump of asymptotics. Yeah. Therefore, at each pole, Zi, this meromorphic connection has internal monodromy data just at this point. If we zoom in this point, it already includes monodromy data at this point, right? So as we said, any solution can have different asymptotics at this point. But we can also think like this, equivalently. We can fix an initial data at this point, at this singularity, fix asymptotics. Then there will be different regions surrounding this pole Zi. And on each region, there is a unique fundamental solution with a given initial data. And these solutions at different regions are in general different. So their ratios are given by Stokes matrices. This is from classical ODE series. Yeah. And here at each pole of degree pi, we have pi pair of Stokes matrices. And these Stokes matrices come in pairs. So half of them are up triangle matrices, and another half is lower. Here, B minus B plus are two opposite Borel subgroups. And then the so-called irregular Riemann-Hilbert map. So this is basically Riemann-Hilbert map, but allowing connections with higher order pole. It's now an analytical map from the configuration space of linear ODEs with fixed number of poles and fixed degree of poles. It's a finite dimensional space to the space of Stokes matrices. Yeah. So basically, this is a Riemann-Hilbert map with a high order pole. And this is a locally analytic isomorphism. This map is very hard to understand because this map is given by highly transcendental functions. Only very few cases have exact formula. For example, when n equal to 2, this map is given by the gamma function computed by Kummer. And it is here. Okay. So any questions on this general setting of Riemann-Hilbert correspondence? And since this Stokes phenomenon is local, we can focus on the case of one pole. So suppose we are given this linear ODE with a k plus 1 over the pole, and U is a semi-simple regular element, and A1 to AK are n-by-n matrices. So a convenient way to describe the module space of these connections is using the truncated affine Lie algebra. So actually, when we fix U, A1 to AK are parameterized by the elements in this truncated affine Lie algebra. So this is basically n-by-n matrix with entries in this ring CT over T power of K. And in this case, the Stokes matrices, the space of Stokes matrices is K multiples of K times of product of set of lower triangle matrices with a space of upper triangle matrix, what I denoted by D minus B minus and D plus. Then Philip Bosch proved that for any fixed U, the now regular Riemann-Hilbert map from the Lie algebra GUN or the dual of the Lie algebra to the product of opposite Borels is actually a Poisson isomorphism, locally Poisson isomorphism. Yeah. So therefore, Peachon and Bosch's theorems put the Riemann-Hilbert maps in a symplectic geometric setup. So, so for any persons on this general setting of Riemann-Hilbert And my goal is to quantize this Riemann-Hilbert map by, since this map is a Poisson isomorphism, so my goal is to find a quantization of these two Poisson varieties, find the two associative algebras, and then an isomorphism between these two associative algebras that quantize this map. Yeah, here let's go to move a bit faster. So here I recall what are the Poisson algebras and what are the quantization. Let's skip this. And then my goal is to, here recall Riemann-Hilbert map is a Poisson map. So the pullback of this Riemann-Hilbert map is just the Poisson algebra isomorphism. Here I use this function. Here, this is bottom line is the dual map, is the pullback of the Riemann-Hilbert map, which is a Poisson isomorphism. Here I take a symmetric function on this D algebra. So this is equipped with the KKS Poisson structure. This is equipped with the, RT, singular RT construction. And my goal is to, so this Poisson algebra, of course, has a canonical quantization by the universal union-looping algebra. Therefore, my goal is to find a quantization of this Poisson space, this Poisson algebra, that is associative algebra, whose semi-constant limit recover this Poisson algebra, and as well as isomorphism between these two associative algebras, such that this diagram becomes commutative. Yeah. In this sense, I quantize this Riemann-Hilbert map. So the Riemann-Hilbert map is a Poisson algebra isomorphism. I want to quantize this Poisson algebras and the isomorphism between them to be a isomorphism between associative algebra. Yeah. So this is what I call quantization of the Riemann-Hilbert map. And of course, this will be highly transcendental. So things here are not algebraic at all. Okay. And why should we care about this quantization? Because after I get this quantization, I can use a representation theory. I can use the representation theory of this associative algebras to solve some classical, analytic problems, like we have seen in the first part, right? In the first part of my talk, I relate to the WKB approximation to the, to the crystal basis theory. So actually, the WKB approximation of linear OD is not known. It's only known for second order case. For higher order case, exact WKB is not known. It's very hard question. But somehow, my idea is to use discrete data to characterize the highly transcendental data. Okay, and so in this bigger framework, we can restate our first theorem in the following setting. So basically, our first theorem gives you a quantization of the Riemann-Hilbert map at the second order pole. So at the second order pole case, recall that our OD is U over Z squared plus A over Z. The parameter space, the diagram space is just the space of A. And the Beatty modular space is the space of Stokes matrices are just the product of two opposite borrows. And the Riemann-Hilbert map is a Poisson map. And on the one hand, the functions, on the one hand, the B plus times B minus is simply the dual Poisson-Lie group. And its quantization is known to be the Greenfield-Jimbo quantum group, so which is a associative algebra as follows. Yeah. And therefore, in this bigger framework, our task is to find. So our task is basically to find associative algebra isomorphism between quantum group and undeformed UGN. So recall that the bottom line is just the Riemann-Hilbert map in second order pole case, which is the Poisson algebra isomorphism. And this functions on the algebra is quantized by universal union-looping algebra, while functions on dual Poisson-Lie group is quantized by quantum group. Therefore, to quantize this irregular Riemann-Hilbert map, we need to find an isomorphism between quantum group and UG, such that its semi-constant limit recovers Riemann-Hilbert map. Yeah. Therefore, our first theorem it's really, it's simply a quantization of the irregular Riemann-Hilbert map at the second order from this viewpoint. And then our second theorem use the representation theory of quantum group, in particular the crystal basis theory of quantum group, to understand, to give some understanding of WKB to the singular perturbation of linear OD. So this is the logic. And of course, we can consider arbitrary of the pole case. It's basically how much time? Yeah, maybe I should, yeah. So similarly, you can consider higher order pole case and use use the you can first consider universal linear OD with the k+1 of the pole, but with non-commutative, variables. Here, this T1 to Tk is a collection of the generators of U, a U of this truncated affine DLD. And you can consider its quantum Stokes matrices now 2K of them. And this 2K quantum Stokes matrices satisfy certain algebraic relations, which define your associative algebra structure. That in turn give you a quantization of the irregular Riemann-Hilbert map. So I think I simply stop here. Thank you very much.
Questions?
Yes, so if you take this, go back to so if you take this K, what's the affinity? So we'll have some map in the young end. Because it seems like if you take this
Yeah, there is young. Well, so when you consider difference equation, you have youngness.
yeah.
But here I don't really know now. But maybe a simpler question is if this module space of meromorphic connection. So basically, if so, this guy is a affine Poisson varieties. If this is a Poisson slice of the affine glass money or the dual affine Poisson equal, yeah, it's a yeah. I don't know if it's not, and then it can go to infinity, right? In some sense. But I think this is a symbiotic slice of the dual affine Poisson equal.
That's okay. Yeah.
Yeah, this is a symbiotic or Poisson geometric reformulation of your question. Yeah. Actually, as far as I know, people don't study this Poisson variety well enough because I asked. So of course you can write down the symbiotic structure on this variety very explicitly using the left and the right Morikawa one form and so on.
Yeah.
It was first written down by Bosch in 2004. But then there is no, as far as I know, there is no matrix formulation. I asked experts like my advisor and some other people, and at least they don't know. Yeah. But I think the first step is to write down R matrix and to compare this R matrix formulation to the affine case. Bosch's formula is very, very explicit, but there is no, algebraic formulation, no R matrix formulation.
You have a very nice table at one of the first slides with various properties of quantum groups related to this analytic formalism. You mentioned also quantum symmetric pairs. I saw it.
Yeah.
Bottom. So for quantum symmetric pairs, there's also now in some cases I crystal theory by Watanabe and others.
Right.
Have you considered trying to generalize in this direction?
So to get the sorry, yeah. Right, to get this to get this I quantum group, you simply quantum symmetric, you simply take okay, this equation. So U is again semi-simple type A, but T is a matrix, for example, type A3 case you take Fij. And this Stokes matrix satisfies the K reflection equation, which give you the quantum symmetry of type A3. But I don't study this H bar because there's a limit, because one can study the same. Well, the problem, there is no, yeah. So there is no, problem here. But as far as I know, there is no. Well, you can define canonical basis for I quantum group, but there is no crystal basis.
Not the same.
Yeah.
Let's say. Not quite the same, but there's some recent paper by Watanabe a few years ago. I crystal theory. It's not as elegant in some sense as the usual crystal theory.
Yeah, because here, if you replace T by F,
Mm.
the fixing locus under the involution,
Mhm.
then the basis you find is simply the Gorham-Hattin basis for type C.
Mhm.
But we know that Gorham-Hattin basis for type C is not the quite right basis because it's not compatible with, because Gorham-Hattin basis for type BCD is not compatible with the hinting diagram. It's, yeah. So there's no, from the analysis viewpoint, there is no new thing. Because, well, for differential equation, GON case is the most hard one. Because others can embed into GON. This is, yeah. Thanks for your question.
Okay, that's central point.
Okay, thanks again.